An explosive material, also called an explosive, is a reactive substance that contains a great amount of potential energy that can produce an explosion if released suddenly, usually accompanied by the production of light, heat, sound, and pressure. An explosive charge is a measured quantity of explosive material, which may be composed of a single ingredient or a combination of two or more. The potential energy stored in an explosive material may, for example, be chemical energy, such as nitroglycerin or grain dust; pressurized gas, such as a gas cylinder or aerosol can; nuclear energy, such as in the fissile isotopes uranium-235 and plutonium-239. Explosive materials may be categorized by the speed at which they expand. Materials that detonate, the front of the chemical reaction moves faster through the material than the speed of sound, are said to be high explosives, and materials that deflagrate are said to be low explosives. Explosives may also be categorized by their sensitivity. Sensitive materials that can be initiated by a relatively small amount of heat or pressure are primary explosives, and materials that are relatively insensitive are secondary or tertiary explosives. A wide variety of chemicals can explode. A smaller number are manufactured specifically for the purpose of being used as explosives. The remainder are too dangerous, sensitive, toxic, expensive, unstable, or prone to decomposition or degradation over short time spans. In contrast, some materials are merely combustible or flammable if they burn without exploding. The distinction, however, is not razor sharp. Certain materials, dusts, powders, gases, or volatile organic liquids may be simply combustible or flammable under ordinary conditions, but become explosive in specific situations or forms, such as dispersed airborne clouds, or confinement, or sudden release. History. At its root, the history of chemical explosives lies in the history of gunpowder. During the Tang dynasty in the 9th century, Taoist Chinese alchemists were eagerly trying to find the elixir of immortality. In the process, they stumbled upon the explosive invention of gunpowder made from coal, saltpeter, and sulfur in 1044. Gunpowder was the first form of chemical explosives, and by 1161, the Chinese were using explosives for the first time in warfare. The Chinese would incorporate explosives fired from bamboo or bronze tubes known as bamboo firecrackers. The Chinese also used inserted rats from inside the bamboo firecrackers to fire toward the enemy, creating great psychological ramifications, scaring enemy soldiers away and causing cavalry units to go wild. Though early thermal weapons, such as Greek fire, have existed since ancient times, the first widely used explosive in warfare and mining was black powder, invented in 9th century in China by Song Chinese alchemists. This material was sensitive to water, and it produced copious amounts of dark smoke. The first useful explosive stronger than black powder was nitroglycerin, developed in 1847. Since nitroglycerin is a liquid and highly unstable, it was replaced by nitrocellulose, TNT in 1863, smokeless powder, dynamite in 1867, and gelignite, the latter two being sophisticated stabilized preparations of nitroglycerin rather than chemical alternatives, both invented by Alfred Nobel. World War I saw the adoption of TNT trinitrotoluene in artillery shells. World War II saw an extensive use of new explosives. See List of explosives used during World War II. In turn, these have largely been replaced by more powerful explosives such as C4 and PETN. However, C4 and PETN react with metal and catch fire easily, yet unlike TNT, C4 and PETN are waterproof and malleable. Applications. Commercial. The largest commercial application of explosives is mining. Whether the mine is on the surface or is buried underground, the detonation or deflagration of either a high or low explosive in a confined space can be used to liberate a fairly specific subvolume of a brittle material in a much larger volume of the same or similar material. The mining industry tends to use nitrate-based explosives such as emulsions of fuel oil and ammonium nitrate solutions, mixtures of ammonium nitrate prills, fertilizer pellets, and fuel oil, ANFO, and gelatinous suspensions or slurries of ammonium nitrate and combustible fuels. In materials science and engineering, explosives are used in cladding. A thin plate of some material is placed atop a thick layer of a different material, both layers typically of metal. Atop the thin layer is placed an explosive. At one end of the layer of explosive, the explosion is initiated. The two metallic layers are forced together at high speed and with great force. The explosion spreads from the initiation site throughout the explosive. Ideally, this produces a metallurgical bond between the two layers. As the length of time the shock wave spends at any point is small, we can see mixing of the two metals and their surface chemistries, through some fraction of the depth, and they tend to be mixed in some way. It is possible that some fraction of the surface material from either layer eventually gets ejected when the end of material is reached. Hence, the mass of the now welded bilayer may be less than the sum of the masses of the two initial layers. There are applications where a shock wave, and electrostatics, can result in high-velocity projectiles. Types. Chemical. An explosion is a type of spontaneous chemical reaction that, once initiated, is driven by both a large exothermic change, great release of heat, and a large positive entropy change. Great quantities of gases are released, in going from reactants to products, thereby constituting a thermodynamically favorable process in addition to one that propagates very rapidly. Thus, explosives are substances that contain a large amount of energy stored in chemical bonds. The energetic stability of the gaseous products and hence their generation comes from the formation of strongly bonded species like carbon monoxide, carbon dioxide, and nitrogen, which contain strong double and triple bonds having bond strengths of nearly 1 mJ/mol. Consequently, most commercial explosives are organic compounds containing NO2, ONO2, and NHNO2 groups that, when detonated, release gases like the aforementioned, e.g., nitroglycerin, TNT, HMX, PETN, nitrocellulose. An explosive is classified as a low or high explosive according to its rate of combustion. Low explosives burn rapidly, or deflagrate, while high explosives detonate. While these definitions are distinct, the problem of precisely measuring rapid decomposition makes practical classification of explosives difficult. Traditional explosives mechanics is based on the shock-sensitive rapid oxidation of carbon and hydrogen to carbon dioxide, carbon monoxide, and water in the form of steam. Nitrates typically provide the required oxygen to burn the carbon and hydrogen fuel. High explosives tend to have the oxygen, carbon, and hydrogen contained in one organic molecule, and less sensitive explosives like ANFO are combinations of fuel, carbon and hydrogen fuel oil, and ammonium nitrate. A sensitizer such as powdered aluminum may be added to an explosive to increase the energy of the detonation. Once detonated, the nitrogen portion of the explosive formulation emerges as nitrogen gas and toxic nitric oxides. Decomposition. The chemical decomposition of an explosive may take years, days, hours, or a fraction of a second. The slower processes of decomposition take place in storage and are of interest only from a stability standpoint. Of more interest are the other two rapid forms besides decomposition, deflagration and detonation. Deflagration. In deflagration, decomposition of the explosive material is propagated by a flame front which moves slowly through the explosive material at speeds less than the speed of sound within the substance, usually below 1000 m/s, in contrast to detonation, which occurs at speeds greater than the speed of sound. Deflagration is a characteristic of low explosive material. Detonation. This term is used to describe an explosive phenomenon whereby the decomposition is propagated by an explosive shock wave traversing the explosive material at speeds greater than the speed of sound within the substance. The shock front is capable of passing through the high explosive material at supersonic speeds, typically thousands of meters per second. Exotic. In addition to chemical explosives, there are a number of more exotic explosive materials, and exotic methods of causing explosions. Examples include nuclear explosives, and abruptly heating a substance to a plasma state with a high-intensity laser or electric arc. Laser and arc heating are used in laser detonators, exploding bridge wire detonators, and exploding foil initiators, where a shock wave and then detonation in conventional chemical explosive material is created by laser or electric arc heating. Laser and electric energy are not currently used in practice to generate most of the required energy, but only to initiate reactions. Properties of explosive materials. To determine the suitability of an explosive substance for a particular use, its physical properties must first be known. The usefulness of an explosive can only be appreciated when the properties and the factors affecting them are fully understood. Some of the more important characteristics are listed below. Sensitivity. Sensitivity refers to the ease with which an explosive can be ignited or detonated, i.e., the amount and intensity of shock, friction, or heat that is required. When the term sensitivity is used, care must be taken to clarify what kind of sensitivity is under discussion. The relative sensitivity of a given explosive to impact may vary greatly from its sensitivity to friction or heat. Some of the test methods used to determine sensitivity relate to: impact sensitivity is expressed in terms of the distance through which a standard weight must be dropped onto the material to cause it to explode. Friction sensitivity is expressed in terms of what occurs when a weighted pendulum scrapes across the material. It may snap, crackle, ignite, and slash or explode. Heat sensitivity is expressed in terms of the temperature at which flashing or explosion of the material occurs. Specific explosives, usually but not always highly sensitive on one or more of the three above axes, may be idiosyncratically sensitive to such factors as pressure drop, acceleration, the presence of sharp edges or rough surfaces, incompatible materials, or even in rare cases nuclear or electromagnetic radiation. These factors present special hazards that may rule out any practical utility. Sensitivity is an important consideration in selecting an explosive for a particular purpose. The explosive in an armor-piercing projectile must be relatively insensitive, or the shock of impact would cause it to detonate before it penetrated to the point desired. The explosive lenses around nuclear charges are also designed to be highly insensitive, to minimize the risk of accidental detonation. Sensitivity to initiation. The index of the capacity of an explosive to be initiated into detonation in a sustained manner. It is defined by the power of the detonator, which is certain to prime the explosive to a sustained and continuous detonation. Reference is made to the cellular Bellet scale that consists of a series of 10 detonators, from N1 to N10, each of which corresponds to an increasing charge weight. In practice, most of the explosives on the market today are sensitive to an N8 detonator, where the charge corresponds to 2 grams of mercury fulminate. Velocity of detonation. The velocity with which the reaction process propagates in the mass of the explosive. Most commercial mining explosives have detonation velocities ranging from 1800 m/s to 8000 m/s. Today, velocity of detonation can be measured with accuracy. Together with density, it is an important element influencing the yield of the energy transmitted for both atmospheric overpressure and ground acceleration. By definition, a low explosive, such as black powder, or smokeless gunpowder, has a burn rate of 171/631 m/s. In contrast, a high explosive, whether a primary, such as detonating cord, or a secondary, such as TNT or C4, has a significantly higher burn rate. Stability. Stability is the ability of an explosive to be stored without deterioration. The following factors affect the stability of an explosive. Chemical constitution. In the strictest technical sense, the word stability is a thermodynamic term referring to the energy of a substance relative to a reference state or to some other substance. However, in the context of explosives, stability commonly refers to ease of detonation, which is concerned with kinetics, i.e., rate of decomposition. It is perhaps best, then, to differentiate between the terms thermodynamically stable and kinetically stable by referring to the former as inert. Contrarily, a kinetically unstable substance is said to be labile. It is generally recognized that certain groups like nitro, NO2, nitrate, ONO2, and azide, N3, are intrinsically labile. Kinetically, there exists a low activation barrier to the decomposition reaction. Consequently, these compounds exhibit high sensitivity to flame or mechanical shock. The chemical bonding in these compounds is characterized as predominantly covalent, and thus they are not thermodynamically stabilized by a high ionic lattice energy. Furthermore, they generally have positive enthalpies of formation, and there is little mechanistic hindrance to internal molecular rearrangement to yield the more thermodynamically stable, more strongly bonded, decomposition products. For example, in lead azide, Pb, N3, 2, the nitrogen atoms are already bonded to one another, so decomposition into Pb and N2 is relatively easy. Temperature of storage. The rate of decomposition of explosives increases at higher temperatures. All standard military explosives may be considered to have a high degree of stability at temperatures from 10 to plus 35 degrees C, but each has a high temperature at which its rate of decomposition rapidly accelerates and stability is reduced. As a rule of thumb, most explosives become dangerously unstable at temperatures above 70 degrees Celsius. Exposure to sunlight. When exposed to the ultraviolet rays of sunlight, many explosive compounds containing nitrogen groups rapidly decompose, affecting their stability. Electrical discharge. Electrostatic or spark sensitivity to initiation is common in a number of explosives. Static or other electrical discharge may be sufficient to cause a reaction, even detonation, under some circumstances. As a result, safe handling of explosives and pyrotechnics usually requires proper electrical grounding of the operator. Power, performance, and strength. The term power or performance as applied to an explosive refers to its ability to do work. In practice, it is defined as the explosive's ability to accomplish what is intended in the way of energy delivery, i.e., fragment projection, air blast, high-velocity jet, underwater shock, and bubble energy, etc. Explosive power or performance is evaluated by a tailored series of tests to assess the material for its intended use. Of the tests listed below, cylinder expansion and air blast tests are common to most testing programs, and the others support specific applications. Cylinder expansion test. A standard amount of explosive is loaded into a long hollow cylinder, usually of copper, and detonated at one end. Data is collected concerning the rate of radial expansion of the cylinder and the maximum cylinder wall velocity. This also establishes the Gurney energy or 2E. Cylinder fragmentation. A standard steel cylinder is loaded with explosive and detonated in a sawdust pit. The fragments are collected and the size distribution analyzed. Detonation pressure, Chapman-Jouguet condition. Detonation pressure data derived from measurements of shock waves transmitted into water by the detonation of cylindrical explosive charges of a standard size. Determination of critical diameter. This test establishes the minimum physical size a charge of a specific explosive must be to sustain its own detonation wave. The procedure involves the detonation of a series of charges of different diameters until difficulty in detonation wave propagation is observed. Massive diameter detonation velocity. Detonation velocity is dependent on loading density, c, charge diameter, and grain size. The hydrodynamic theory of detonation used in predicting explosive phenomena does not include the diameter of the charge, and therefore a detonation velocity, for a massive diameter. This procedure requires the firing of a series of charges of the same density and physical structure, but different diameters, and the extrapolation of the resulting detonation velocities to predict the detonation velocity of a charge of a massive diameter. Pressure versus scaled distance. A charge of a specific size is detonated and its pressure effects measured at a standard distance. The values obtained are compared with those for TNT. Impulse versus scaled distance. A charge of a specific size is detonated and its impulse, the area under the pressure time curve, measured as a function of distance. The results are tabulated and expressed as TNT equivalents. Relative bubble energy, RBE. A 5 to 50 kg charge is detonated in water and piezoelectric gauges measure peak pressure, time constant, impulse, and energy. The RBE may be defined as Kx3. RBE equals Ks, where K equals the bubble expansion period for an experimental, X, or a standard, S, charge. brisance. In addition to strength, explosives display a second characteristic, which is their shattering effect or brisance, from the French meaning to break, which is distinguished and separate from their total work capacity. This characteristic is of practical importance in determining the effectiveness of an explosion in fragmenting shells, bomb casings, grenades, and the like. The rapidity with which an explosive reaches its peak pressure, power, is a measure of its brisance. Brisance values are primarily employed in France and Russia. The sand crush test is commonly employed to determine the relative brisance in comparison to TNT. No test is capable of directly comparing the explosive properties of two or more compounds. It is important to examine the data from several such tests, sand crush, Troslow, and so forth, in order to gauge relative brisance. True values for comparison require field experiments. Density. Density of loading refers to the mass of an explosive per unit volume. Several methods of loading are available, including pellet loading, cast loading, and press loading, the choice being determined by the characteristics of the explosive. Dependent upon the method employed, an average density of the loaded charge can be obtained that is within 80–99% of the theoretical maximum density of the explosive. High load density can reduce sensitivity by making the mass more resistant to internal friction. However, if density is increased to the extent that individual crystals are crushed, the explosive may become more sensitive. Increased load density also permits the use of more explosive, thereby increasing the power of the warhead. It is possible to compress an explosive beyond a point of sensitivity, known also as dead pressing, in which the material is no longer capable of being reliably initiated, if at all. Volatility. Volatility is the readiness with which a substance vaporizes. Excessive volatility often results in the development of pressure within rounds of ammunition and separation of mixtures into their constituents. Volatility affects the chemical composition of the explosive such that a marked reduction in stability may occur, which results in an increase in the danger of handling. Hygroscopicity and water resistance. The introduction of water into an explosive is highly undesirable since it reduces the sensitivity, strength, and velocity of detonation of the explosive. Hygroscopicity is a measure of a material's moisture-absorbing tendencies. Moisture affects explosives adversely by acting as an inert material that absorbs heat when vaporized, and by acting as a solvent medium that can cause undesired chemical reactions. Sensitivity, strength, and velocity of detonation are reduced by inert materials that reduce the continuity of the explosive mass. When the moisture content evaporates during detonation, cooling occurs, which reduces the temperature of reaction. Stability is also affected by the presence of moisture since moisture promotes decomposition of the explosive and, in addition, causes corrosion of the explosive's metal container. Explosives considerably differ from one another as to their behavior in the presence of water. Gelatin dynamites containing nitroglycerin have a degree of water resistance. Explosives based on ammonium nitrate have little or no water resistance due to the reaction between ammonium nitrate and water, which liberates ammonia, nitrogen dioxide, and hydrogen peroxide. In addition, ammonium nitrate is hygroscopic, susceptible to damp, hence the above concerns. Toxicity. Many explosives are toxic to some extent. Manufacturing inputs can also be organic compounds or hazardous materials that require special handling due to risks, such as carcinogens. The decomposition products, residual solids, or gases of some explosives can be toxic, whereas others are harmless, such as carbon dioxide and water. Examples of harmful byproducts are heavy metals, such as lead, mercury, and barium from primers, observed in high-volume firing ranges. Nitric oxides from TNT. Perchlorates when used in large quantities. Green explosives seek to reduce environment and health impacts. An example of such is the lead-free primary explosive copper, I,5-nitridetrazolate, an alternative to lead azide. One variety of a green explosive is Cdp explosives, whose synthesis does not involve any toxic ingredients, consumes carbon dioxide while detonating and does not release any nitric oxides into the atmosphere when used. Explosive train. Explosive material may be incorporated in the explosive train of a device or system. An example is a pyrotechnic lead igniting a booster, which causes the main charge to detonate. Volume of products of explosion. The most widely used explosives are condensed liquids or solids converted to gaseous products by explosive chemical reactions and the energy released by those reactions. The gaseous products of complete reaction are typically carbon dioxide, steam, and nitrogen. Gaseous volumes computed by the ideal gas law tend to be too large at high pressures, characteristic of explosions. Ultimate volume expansion may be estimated at 3 orders of magnitude, or 1 liter per gram of explosive. Explosives with an oxygen deficit will generate soot or gases like carbon monoxide and hydrogen, which may react with surrounding materials such as atmospheric oxygen. Attempts to obtain more precise volume estimates must consider the possibility of such side reactions, condensation of steam, and aqueous solubility of gases like carbon dioxide. By comparison, Cdp detonation is based on the rapid reduction of carbon dioxide to carbon with the abundant release of energy. Rather than produce typical waste gases like carbon dioxide, carbon monoxide, nitrogen, and nitric oxides, Cdp is different. Instead, the highly energetic reduction of carbon dioxide to carbon vaporizes and pressurizes excess dry ice at the wave front, which is the only gas released from the detonation. The velocity of detonation for Cdp formulations can therefore be customized by adjusting the weight percentage of reducing agent and dry ice. Interestingly, Cdp detonations produce a large amount of solid materials that can have great commercial value as an abrasive. Example: Cdp detonation reaction with magnesium, XCO2 plus 2 mg 2 MgO plus C plus, X1, CO2. The products of detonation in this example are magnesium oxide, carbon in various phases including diamond, and vaporized excess carbon dioxide that was not consumed by the amount of magnesium in the explosive formulation. Oxygen balance, OB% or omega. Oxygen balance is an expression that is used to indicate the degree to which an explosive can be oxidized. If an explosive molecule contains just enough oxygen to convert all of its carbon to carbon dioxide, all of its hydrogen to water, and all of its metal to metal oxide with no excess, the molecule is said to have a zero oxygen balance. The molecule is said to have a positive oxygen balance if it contains more oxygen than is needed and a negative oxygen balance if it contains less oxygen than is needed. The sensitivity, strength, and brisance of an explosive are all somewhat dependent upon oxygen balance and tend to approach their maxima as oxygen balance approaches zero. Oxygen balance applies to traditional explosives mechanics with the assumption that carbon is oxidized to carbon monoxide and carbon dioxide during detonation. In what seems like a paradox to an explosives expert, cold detonation physics uses carbon in its most highly oxidized state as the source of oxygen in the form of carbon dioxide. Oxygen balance, therefore, either does not apply to a Cdp formulation or must be calculated without including the carbon in the carbon dioxide. Chemical composition. A chemical explosive may consist of either a chemically pure compound, such as nitroglycerin, or a mixture of a fuel and an oxidizer, such as black powder or grain dust and air. Chemically pure compounds. Some chemical compounds are unstable in that, when shocked, they react, possibly to the point of detonation. Each molecule of the compound dissociates into 2 or more new molecules, generally gases, with the release of energy. Nitroglycerin, a highly unstable and sensitive liquid. Acetone peroxide, a very unstable white organic peroxide. TNT, yellow insensitive crystals that can be melted and cast without detonation. Cellulose nitrate, a nitrate polymer which can be a high or low explosive depending on nitration level and conditions. RDX, PETN, HMX, very powerful explosives which can be used pure or in plastic explosives. C4, or composition C4 and RDX plastic explosive plasticized to be adhesive and malleable. The above compositions may describe most of the explosive material, but a practical explosive will often include small percentages of other substances. For example, dynamite is a mixture of highly sensitive nitroglycerin with sawdust, powdered silica, or most commonly diatomaceous earth, which act as stabilizers. Plastics and polymers may be added to bind powders of explosive compounds, waxes may be incorporated to make them safer to handle, aluminium powder may be introduced to increase total energy and blast effects. Explosive compounds are also often alloyed, HMX or RDX powders may be mixed, typically by melt casting, with TNT to form octol or cyclotol. Mixture of oxidizer and fuel. An oxidizer is a pure substance, molecule, that in a chemical reaction can contribute some atoms of one or more oxidizing elements, in which the fuel component of the explosive burns. On the simplest level, the oxidizer may itself be an oxidizing element, such as gaseous or liquid oxygen. Black powder, potassium nitrate, charcoal, and sulfur. Flash powder, fine metal powder, usually aluminium or magnesium, and a strong oxidizer, e.g. potassium chlorate or perchlorate. Aminol, ammonium nitrate and aluminium powder. Armstrong's mixture, potassium chlorate and red phosphorus. This is a very sensitive mixture. It is a primary high explosive in which sulfur is substituted for some or all of the phosphorus to slightly decrease sensitivity. Cold detonation physics, combinations of carbon dioxide in the form of dry ice, an untraditional oxygen source, and powdered reducing agents, fuel, like magnesium and aluminum. Sprengel explosives, a very general class incorporating any strong oxidizer and highly reactive fuel, although in practice the name was most commonly applied to mixtures of chlorates and nitroaromatics. ANFO, ammonium nitrate and fuel oil. Chadites, chlorates or perchlorates and oil. Oxoliquids, mixtures of organic materials and liquid oxygen. Panclastites, mixtures of organic materials and dinitrogen tetroxide. Availability and cost. The availability and cost of explosives are determined by the availability of the raw materials and the cost, complexity, and safety of the manufacturing operations. Classification of explosive materials. By sensitivity. Primary explosive. A primary explosive is an explosive that is extremely sensitive to stimuli such as impact, friction, heat, static electricity, or electromagnetic radiation. Some primary explosives are also known as contact explosives. A relatively small amount of energy is required for initiation. As a very general rule, primary explosives are considered to be those compounds that are more sensitive than PETN. As a practical measure, primary explosives are sufficiently sensitive that they can be reliably initiated with a blow from a hammer. However, PETN can also usually be initiated in this manner, so this is only a very broad guideline. Additionally, several compounds, such as nitrogen triiodide, are so sensitive that they cannot even be handled without detonating. Nitrogen triiodide is so sensitive that it can be reliably detonated by exposure to alpha radiation. It is the only explosive for which this is true. Primary explosives are often used in detonators or to trigger LAR.
Please subscribe and thanks for watching.